At least you started. That's a good sign. At least. Good.
Yes, yes.
Okay, Mr. Cedeño, Axel Cedeño.
Good morning,
Axel
doctor.
Cedeño. Good morning. How are you? Where are
Fine,
you?
thank you.
Where are you right now?
Guayaquil.
Oh, good. You ready for next week?
Uh, more or less.
You have to come next week, okay? Yeah. And yeah, we're gonna have labs. We've been very busy with Ms. Sayo, Mr. Miranda, preparing the experiment. Everything is ready, right, Daniela Sayo?
Yes, doctor, it's ready.
Okay, so the experiment is ready. We're gonna do 2 tests with the same equipment, and the idea is to try to see the influence of shear in bending. You'll see, it's very interesting. Okay, people. Ms. Sayo, would you please start recording?
Okay, doctor.
Okay, good. Morning, students. Today is June the 2nd. Wow. And right now I'm in the lab at the university, and we're going to basically complete the material that we have for this first part of the semester. So we're going to complete the example that we had, and then we are going to do a new example. This new example, I took it from Popov's book, and I Can you hear me now? Can you hear me?
Yes, doctor.
Okay. I'm sorry about this. I don't know what's happening, but even though I'm connected through the internet, there's some problem. And anyway, so let's go on with our material. Okay. So I'm going to share this. Okay. Screen swap. Can you see my full screen, people?
Yes,
Okay,
doctor.
okay, good. Site. And so we were analyzing this I-beam in last session, okay? And the one suggestion is that when you do this analysis, you do a clear sketch, so you can see equilibrium. That's the beauty about the Newton's equilibrium law, right? Because you need to see forces, and forces gets you or take you to equilibrium, okay? So we said that here we could have for example, if we want to analyze a segment, okay, define it or starting at cut A, right? So you see here that we have a segment, right? This segment here. And this segment, okay, starts here and goes all the way up to this edge. And this edge is free. So tau here, it would be tau zx would be 0 because it's open, right? So this is the sector. In this sector, we have an axial force. And because of this axial force is not equilibrated, we need tau sx on this cut, right? Now this tau is equal to this one, but this is something that we explained. Tau yx is equal to tau xy. That's because we need to have equilibrium of momentum. That's something that you studied in solid mechanics, right? Now, we can do something similar, but we can consider the cut B. B is here. Again, we go in this direction. So we started here and we go all the way up to here because this edge is, again, is free. So every time we apply this relation, we have only one unknown. And the unknown that we are trying to find, or we can find because we have only one equation, is the tau at the point where we make the cut and we start the integration. We calculate with the formula that we have deduced. We have only one formula. We can calculate at the cut, the tau. And we integrate from there all the way, okay, defining this sector. And the sector ends in the point where we know the value of the stress. The value of the stress at the edge is 0. We know that value. So we have one equation, and we can apply it to get one unknown. In this case, is tau, right? So we have to be very careful with that, okay? Because the directions are very important. Okay, so we have this direction, and that would be tau xs, like that, okay? And then this is the opposite of this one, and it has an explanation. Then we can go and make a cut at C down here, okay? And again, we start here and we consider all of this as the sector. So we have this line, cross area, and we're going to determine the stress in that cut, right? Because here and here, tau is 0. Again, this is the direction of the stress because this is a negative phase, right? This is something which is very interesting, okay? We could analyze again the stress down here at card D, right? And similarly with the other cases, okay? This is card D, and it's very interesting because if we define this sector, okay, from here all the way up to here and here, of course the stress here is zero. The stress here is zero. The stress here and here in D prime are the same because of symmetry. So we have one equation and one unknown. Okay, and then we can go on. We can go on and calculate the shear stress. But this sector is very large. So the integration includes several terms. So some of you make a comment that it would be very nice if instead of integrating all of this cross area, we could integrate only this little piece here. And it is possible, right? Because if we consider this and that, together with everything else would give us the integration of Q would give us zero. Because remember, that's the condition because we have no net axial force on the whole section, right? And then in chapter 1, we concluded that the only possibility that this would be zero when we integrate the normal stress over the whole section was that the origin, this origin, would be located at the centroid of the section. So we can take advantage of that. So if we integrate Q over the whole section, will give us zero. Okay, so this little piece is the same as the integration for the whole thing, or this cross area, which is much larger, to complete the integration with the negative sign. Okay, so that's very useful. And that's what we did here. Okay, so in this case, this piece, this element, Q of S, is negative. Okay, for this segment. Okay, so that's the N, because S goes in this direction. Okay, so if this is negative, the positive should go in the other direction. But because of this negative, we have to point it like this. You see that it points in that direction, XS. Okay, so this is much, much easier. Instead of integrating all of this, all of that, and the upper flange. It's much, much easier. Okay, so that's what we did on Tuesday. Let's go on. Oh, this is the summary. This is the summary. Okay. We see that it's something which you have to have in your mind. Okay. In our chapter, we are considering only forces, external forces in the vertical direction. Okay. So we have a beam like this, and we have a force like this, a force like that. So there is no forces in the X direction. So if we make a cut in any place that we want, okay, P, this is the axial force, is identically zero. Similarly, forces in the Z direction, let's call it V sub Z, they have to be equal to zero. Why? Because there is no forces in the Z direction. Okay, so here in this section, okay, instead of applying the shear force, we are converting that into a distribution of stresses. Okay, so since we have no shear force in the Z direction, okay, we have to see that the integration of the stresses in the z direction give you 0. Okay, so otherwise we will have no equilibrium. And this is what we see here. No? On this flange, we see that we have a net force pointing to the left in the positive z direction. But on the other side, we have something similar, but pointing in the y direction. Okay, then we say this cancels that, and we have no net force from the flange in the upper direction, in the upper flange. Similarly, you see that here, integrate this, and you get a force in the negative z direction. Similarly, on the other side, this will give you a positive force in the z direction. But these two cancel out. So there is no net force in the z direction. And then we have, of course, the stresses in the vertical direction. And you integrate that, and you should get a force equal to the shear force. Because what you are doing, remember, is instead of applying single force on the section, we are taking or converting that into a distribution of stresses. So we took the bending moment and converted into a distribution of stresses, right? Linearly varying. And now we take the shear force and we convert it into a distribution of shear stresses. It's statically equivalent. Remember, shear force, bending moment, they have to have a certain value because those come from equilibrium. Okay. This is something which is just a summary of all of this information. We make cuts at different points. In the flange, the variation is linear. On the web, the variation is quadratic. And what I've done here is on the right-hand side, the last two columns, I integrated, right, on the vertical element. And this is something that you have to do with no numbers, but with variables. And you have to show me, you have to prove yourself that it's indeed, you recuperate the value of V. Okay, that's what we are obtaining here. And we are using Simpson integration rule since we have no explicit expression for the distribution of tau. That's with expression, explicit expression, you have to do it in the assignment. Okay. This is like the summary of all this information that we have obtained. Okay. This is on the left-hand side, we have the section, it's an I section. Here, this is something very typical of this, is typical of this part of the material, okay? So this part here, okay, that's a distribution of stress on the flange. This is the flange. So this part here corresponds to this. And then this part here corresponds to the web. Okay, so this is this part up to here only, because this is symmetric. Okay, and you see that you start here in 0. Okay, and I'm sorry, I'm plotting in this direction, I'm plotting tau, xs. Okay. Okay, and in the vertical direction is the distance from the neutral axis. So, so you start here, and you go in this direction. You increase. You go from 0 up to here. So this is the shear stress at this cut. Just a little bit to the left. So in this case, this is the area, this is the sector that you include, that you consider. Okay? Now, if we make a cut just here, the sector now includes the other side. Okay, if you make a cut here, this is the value that you obtain. If you make a cut here, you have to include both sides, and this is the value that you obtain. So this cut here is the value that you obtain when you make this cut. And this value here is the value that you obtain if you make this cut. There is a jump. Okay, and that's, if you do this analysis, considering not the shear stress, but the shear flow, you will see that it's some sort of continuity. See, you go up, it's like a big pipe, right? And then you split in twice. So you go half on one side and the other to the other side. So if you make this plot, instead of the shear stress, you plot shear flow. In that case, okay, this value here will be twice this value here. Because on one side, you consider only this flange, and in this cut, that's the reason they call it shear flow. And from this point, you can see that you increase or you vary quadratically. Okay, you have a maximum on the neutral axis, and then you start decreasing in a symmetric way in this part here. Okay. Any questions about these people? Any questions?
Good morning,
Okay.
user. I have a question.
Yeah, go on.
In the case that we have on the flange, the other side, the right-hand side, is going to be the same like in the beginning of the left.
Yeah, exactly.
It should be like a two triangles.
Yes. Yes.
And
But
then
well, it's a bit difficult. So we plot it on
for example,
these are arrows. Maybe they are too small, you can see it, but these are arrows and they are pointing to the right. These are arrows. And here, these arrows point to the left. Why to the left, why to the right? Because they have to cancel. Because you cannot have net force in the z direction.
okay, thank you.
Okay? No problem, no problem. Okay, so let me ask you a question, okay? Let's keep thinking about this I section, okay? So is it possible this shear stress distribution? So let's suppose I have a section, this, and let's do this. Okay, let me put shear stresses to the right on the top, and let me put shear stresses to the left here. They cancel, right? Is it possible? Is it possible, people? See, you have on the top, you have a net force pointing in that direction. On the bottom, you have a net force pointed in the opposite direction. They cancel. Is it possible? Instead of this, I propose this. The question is why this is not possible. Think in static equilibrium terms.
we're going to have a bending moment.
No bending moment. Bending moment would be in the Z direction. What's the moment that you have? You're correct. You're going to have a net moment, but in what direction?
But in what, in X?
X.
In X direction. That's a torsional moment. And you have no torsional moment because you are only having vertical loading. So in this case, that's not possible. Now, if you had torsional loading, yes, that's possible. But in this case, no. Why not? Because we have no torsional load. Okay, so let me complete this. Okay. So this is X direction. So this is Z direction. And vertical, this is Y direction. Okay, so in this case, we would have a net torsional moment. But we have not applied any torque. So it is not possible. It's not possible. Okay? No questions. Okay, now let's go to the next example. Okay, I took it from Popov's book. Okay, it's a wooden beam, 2 supports and one with one force concentrated on its end. The calculation of the distribution of the shear force, that's not a problem here because that's part of the chapter 1. You're supposed to be able to solve that. If you are not able to solve quickly the distribution of the shear force, you are not up to the point where you are supposed to be, because that's part of the chapter 1, and chapter 1 is just a review from the previous course. Okay, so I'm concentrated right now in chapter 2. That's shear stresses. So this is the beam that we're going to analyze. Okay, so it's the beam, 2 supports, and on the end, on the right end, we have a concentrated force of 950 pounds. Okay, so if you apply this loading on the right end, of course, the reaction at the left is going to point downward, and the reaction at B is going to be upward. I'm not going to do this calculation. You are supposed to be able to do it, okay? If you are not able to do it, please pay attention because you are behind, okay? So we're gonna have this force pointing downward, and this point pointing upward, and this point downward. This reaction be with A and on the end. So make sum it up, give the spot of B. Okay, so it's like it's okay. Now, called board A. Okay, on the side, I have a board B. Here, board B. Connecting the 2 sides, I have a board C. Okay? And since each one of these is an independent piece, this is dependent of that. They put it together, and what we do is we use nails, okay, to join all of these boards. Okay? So all of these things, these are nails that we're going to be calculating. Okay, these are nails. For example, this nail here connects board A with board B. Okay, this nail connects A with B. Okay, this here, for example, connects board D with board C. There are going to be some nails also connecting the B with this, and finally there will be some upward, right? Instead of like this being like that, connecting the bottom board with the B and D boards. Okay, are we clear with these people? So it's like having several okay, it's very long board. That's one. That's board A. Okay, and you have a different board like this. It's going to be board B. Okay, so we put it together and then we use nails in order to join them. And the nails will have to sustain the shear stresses at the different locations. And that's what we are going to calculate. How many nails do we need? Okay, that's the objective exercise. Dimensions: wide is 10 inches, in height is 14. Okay, so each one of these boards is 2 inches thick, so it's about this thick. How many centimeters do we have in this? 2 inches. Mr. Jangare, how many centimeters do we have is the thickness of every board in this example? Mr. Jangare, how many centimeters? 2 inches. How many centimeters?
Approximate 4.5. No, 6 centimeters. 5 centimeters.
About five.
5.
Okay, show me 5 centimeters with your fingers. Show me 5 centimeters. It's like this. It's like this. Show me 5 centimeters. Mr. Jangare, with your fingers, show it to me. Is this? Yes, that's about that. Yeah. We have to start thinking physically. Okay? You have to start thinking physically. So try to imagine right now a board 5 centimeters thick. Okay? That's like this. And there is another one which is going to be vertical like that. And the two will be joined by nails. For example, if you have to think more or less how many millimeters would have the diameter of a nail? Somebody tell me, how many millimeters do you think that a nail has? A nail that you use to work with wood. How many millimeters do you think has the diameter?
2, maximum 3.
It's about 3 millimeters. Yeah, it's about this thing. This thing. I mean, the diameter is about that big. Okay? We can presume that it is steel. So that's the problem. Okay? Now let's go on. Here, I have the distribution of the shear force. I'm not going to discuss it. You have to be certain that you know how to calculate this. Okay? So I'm going to take here. See, this is positive. Then we have a jump, and then we have a negative value here. Okay, so this is a larger value. So I'm going to take a cut here, and we're going to do the shear stress analysis of this beam section. And what we need to know is how many nails do we need to include? Because see, the shear will try to make it slide one over the other, right? That's the action of the shear. So what we have to do is we have this piece and this other piece. What we have to do is put something between them. So if it tries to slide, it cannot. Why not? Because we have enough nails. Okay. If we have too many nails or too small nails, what happens? the two boards will slide one over the other, and the thing will fail. And we don't want that, okay? So we have several pieces, and we have to join. So we're going to calculate how many nails do we need in order to connect board A and board B. And then we're going to do something similar to connect board B and board C, okay, without formulations. Okay, now let's do it. So we're seeing that in the area between the two supports, we have the largest shear force. In that area, we are going to concentrate. Okay, now, if we have the connection between boards A, that's flat, and board B, that's vertical, can you calculate the shear stress in this cut, in the connection? Can you calculate the, oh man, where am I? Can you calculate the shear stress here, people? The problem here is that we do not know and where we can assume that the shear stress is null. That's the problem here, okay? So let's say one word about that. So we said before that we need to have net forces in the Z direction equal to 0, right? And we have to have net forces in the Y direction equal to, in this case, 1,900 pounds, right? So if we have shear stress on this part, okay, on the board A, that will give us a force pointing in the minus Z direction. But we need to cancel. So how can we do it? The only way what we have is to have another stress in this direction. So on one side points to the right and the other points to the left, and then we cancel. But the problem is that we have to calculate the first moment. But the first moment is a continuous function. How can we change sign in going from the left side of the flange to the right-hand side of the flange? The only way that we can do it is if we have this stress on the left-hand side to decrease. And when we go through the symmetry axis, the value of the shear stress has to value 0. And then on the other side, we're going to have the stress, but with a different sign. So that means that if we move here to the right, the shear stress is smaller. On the symmetry axis, it will value 0, and then we change sign. So this one here will be smaller, but pointing in the opposite direction. So we decrease to 0, and on the other side, we have different sign. So that means that on the symmetry axis, on the y-axis, the shear stress has to be 0. Otherwise, we will have no cancellation in the Z direction. Okay, so let me write down here, since we need to have dz equal to 0, okay, the shear stress, the flanges varies linearly, and having a zero value at y-axis. Okay, let me draw this in a better way so we can see what I'm saying. So here I will have this, then will decrease, then will decrease. And on the other side, we have similarly, but pointing in the opposite direction. So you see that if we integrate this, we're going to have a force in the z direction, okay, but pointing to the right. And on here, we'll point to the left, and these two will cancel. That's what we need. That's what we need. Now, on the vertical boards, we're going to have shear stress like this, and you see that it's going up, 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 and it just bends to the right, and it's pointing in the same direction. If you want to change direction, that means that you have to go down to zero, and then we change sign and we start increasing, but in the opposite direction. Okay, so you go up, 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 change sign, and then you go like this, and on the other side, you will have something like this and like this. Okay, and this is going to be equal to that one. This is going to be like that one. But, okay, from each one of the webs, you will have the contribution pointing upward. And then it bends. And the only way you have continuity is like having on the symmetry line, both distribution being equal to zero. So you go up, start reducing, zero, and then you start decreasing, but in the opposite direction. And then on the other web, you also have shear stress pointing upward. So the contribution from both webs helps to reproduce the value of the shear force. Okay, so you integrate on the web on the left, integrate on the web on the right, and you add these two, and you should recuperate 1,900 pounds. Okay. Similarly, you can reason for the bottom. Okay, for the bottom, let's go to the bottom. Bottom, you start decreasing, and then you start going to the left, smaller, smaller, and then you change sign. So here you will have pointing to the right, pointing to the right, pointing to the right. Okay, and here pointing upward. So all of these will produce a net force in the vertical direction. So here you have a force in the vertical direction, force in the vertical direction. Here, force in the X direction, in the Z direction, force in the Z direction. So this cancels that. And this one here plus this one here will give you the shear force on the section. Mr. Zurita, how do you feel?
Good morning, doctor.
Good morning.
Shear force is direction Y.
Yes. Shear force is in the Y direction. Yes.
Because why not is cancels
Because
the other shear
No.
stress in B with D.
okay,
the web.
let's remember that. Okay, here on this beam, this is X direction, this is Y direction. Okay, if we make cut here, okay, let me draw in a simple way. This is your beam. This is the X direction. This is the Y direction, and this is the Z direction. So you're seeing that you have a force pointing downward in the y direction. So you can imagine any distribution of stress on the section, but you integrate those stresses, you will get forces, internal forces. And the only internal force that we are trying to recuperate here is V. And V points in the y direction, in the upward y direction. That's why we are saying is that since we have no forces in the z direction, the shear force integrating the shear stresses has to cancel because there is no force. Okay, for example, here, okay, more or less here, you have the reaction, this one here, and more or less about here, you have the other. This is reaction in A, this is reaction at B. So you have only forces in the y direction. If you have a net force in the z direction on this cut, you're in trouble. Because if you have only one force in the z direction, there is no way you can have equilibrium. So that's why if you integrate the shear stresses on the sections in the z direction, in this chapter, they have to be zero. Why? Because there is no forces in the z direction in these examples. In the general world, yes, you could have forces in the z direction. And in that case, probably what you can do is you can do two analyses. One for the forces in the y direction and one for the forces in the z directions. And at the end, you simply add them up, assuming that the problem is linear. Mr. Zurita?
Okay, doctor, I understand.
Okay.
Thank you.
Anybody else, please? Let me see if we can. Mr. Soria, good morning. Are you with me, Mr. Soria?
Good morning, doctor.
Good morning. Are you with me?
Yes.
Sure.
So.
Okay. Okay. Let's check if you are with me or not. Okay. For example, right now, let's consider that we want to calculate the shear stress at the connection between boards A and B. How would you do that, Mr. Soria? I want to calculate the shear stress in the connection between A and B, boards A and B. How would you do it?
With the shear flow.
Okay, how much is the shear flow? Do you remember the formulation for the shear flow?
B.
Okay. Come on, man.
For Q divided
Divided by
the inertia.
exact sectional inertia.
Inertia B.
No, inertia not B, just inertia. If you divide it by B, then you have shear stress. You said shear flow. Okay, how would you calculate Q? How would you calculate Q?
Q is the area or
times position of the centroid. Okay, with this dimension, can you see the dimensions? Can you tell me what's going to be the area of the sector?
So the sector is the connection between A and B.
That's the point. I mean, you have to define a cut, and then you have to integrate all the way up to a point where you know the shear stress. Okay, let me ask somebody, Mr. Dominguez, Alim Dominguez, what would be your sector for the integration? What would be your sector, Mr. Dominguez?
It will be the half A.
No. Please listen to my question. What would be the sector that you are going to consider in order to calculate the shear stress at the connection between boards A and B? What would be the sector? Remember, let me go back. See, when we do this, you see here, for example, on the left-hand side, you see that we cross an area. Here, you see this is crossed. So this is our sector. And in this sector, we calculate the imbalance force. And from that point, we go on and calculate the shear stress. Okay? My question now is, in this case, what is the sector that you are going to be considering to calculate the shear stress in this cut in here?
But you need the numbers or
No, describe it to me. Where do you start and where would you finish? Of course, you will start here. And where would you finish? You can go all the way. Anybody? Where would you go with the integration?
I think that we want to go to the left-hand side, maybe to the half of the flange A.
Why only half?
Because we know that in the other side, we have the same arrows, but in the different direction.
No, that's not the reason. Up to here, that's correct.
Because we have another nails in the other.
No, that's not. Remember.
Because it's 0 in this point.
That's the answer. That's the answer, right? Because if we cut here, we're going to have a shear stress in this cut with a certain value. And if we make a cut here and we do not know the value on this cut, we're going to have two unknowns, but we have only one equation. So we have to define our sector starting at the point where we want to calculate the shear stress. And in the other side, we have to go all the way up to a point where we know the shear stress. Yes, you're correct. I don't know who answered, but yeah, that's the correct answer. We go all the way up to the symmetry line because in there, the shear stress is null. Okay, let's do that. That's the next step. I don't know, for some reason. Okay, the animation went wrong. You were not supposed to see this yet. But anyway, it's here, so you can see it. I try to identify the sector that we're going to be analyzing, okay? So this is a sector. It starts here and it ends up here. Why? Because as somebody said, in this cut, the shear stress would be 0. So we have only one unknown, which is below this cut, okay? So this shear, okay, this is the value, we're gonna see that in the details in a second, will be overcome by the nails. And knowing the strength of the nail, we will be able to determine how many nails do we need. Okay, we're going to do that when we return, okay? So think about how to calculate all of these properties in order to evaluate the stress, okay? We'll be back in 5 minutes because I need a break for my throat, okay? 5-minute break, people, and then we will go on.